why you should learn it, but today the focus will be on slant asymptotes or even parabolic asymptotes. Have you done any with slant asymptotes? Okay, so that's new. So she didn't teach ahead of time. That's cool. It's pretty maybe 80% of the same old stuff. All the inside stuff when you go to graph this, it's the same. The holes, the asymptotes, the vertical asymptotes, the x-intercepts, all the same. The end issue, the end behavior is where it becomes different, all right? So let's get into that and review a couple of the main ideas. Say you looked at this bad boy. Let's first factor it. I think if you factor it, you get something like that. And right away, that's not what I wanted. Can you change that to 3 because I don't have a big enough scale to show that point. Can you change that to 3 minus x? Do you mind? Anything for you, Mr. Rickman? All right. How do you know if there's a hole in it? There's a 0, 0. Common factor 0, 0. Okay, resulting in a 0 over 0. That's a hole. True that. In this case, we have a common factor. So you know that the x is at 0. I think you'll agree that there's a hole at x equals 0. If there's a hard part to this, it's the y. What's the y of the hole? How do you find the y coordinate to the holes? Plug it back into the original or the hole removed equation? Hole removed equation. Basically, you're evaluating the limit. To find the y for the hole at x equal a, you're really saying, what's the limit as x goes to a of the function? And that's the hole removed case. In order to evaluate the limit, you'd say, well, I can't do it yet, but if I cancel out that x, then I can direct substitute. And in this case, the hole is at -4/3. Sweet. So, while I haven't graphed a single point of what it is, I can graph what it isn't, which is 0, -4/3. I have a hole. Okay? Mm-hmm. All right. Again, I know this is a review, but the numerator zeros, what does it tell you about the graph? X-intercepts. And what do the denominator zeros tell you? Vertical asymptotes. So this graph then has a horizontal asymptote at, or sorry, a x-intercept at 4 and a vertical asymptote at 3. Do you agree?
Yes.
Good. Okay. Now in terms of outside or end behavior, the end behavior could go, I really think of it as 3 different scenarios. If there's more power in the denominator, then as x gets large, the function will go to 0, right? Mm-hmm. If the function goes to 0, then y goes to 0. And if y goes to 0, then graphically you're looking at what? Horizontal asymptote at y equals 0, also known as the x-axis. Okay? If there's more denominator power, then the results approach 0, and the graph will approach the x-axis. If there's equal power in the numerator and denominator, as in this case, then the function will approach a constant. And by constant, I mean not 0 constant, like some other constant. Then there would be a horizontal asymptote at y equals c. Now, this is the topic of today. If x goes to infinity and y goes to plus or minus infinity, then, well, gosh, it could go to infinity a lot of ways. It could go in a linear way, in which case there's a slant asymptote. It could actually go to infinity in a parabolic way. There could be a parabolic asymptote or a cubic asymptote. You could get a lot of different asymptotes, but you'll definitely be getting either a slant asymptote or parabolic. Might as well put that in. We'll do a case like that, etc. But to find it, you must divide to find it. One of 3 ways. And I apologize if I didn't give you anywhere close to enough room in that note box to get that down. Okay? When I say divide it, you'll actually be dividing possibly 3 different ways. Okie dokie. So let's get into a few examples, and by a few, I think I have 5. Let's finish this. What's the end behavior here? The limit as x goes to infinity of that function is?
-1.
Negative 1. Okay? That means then that the graph has a horizontal asymptote at negative 1. This doesn't tend to coop BC students out as much as my pre-calculus students out, but people think, well, asymptotes, they can never be crossed. Is that the case? It's not the case. For vertical asymptotes, it's the case. But for horizontal asymptotes, when we found that a horizontal asymptote, we just did it by taking x to infinity. This is behavior as x goes to infinity. This is only behavior on the outside of the graph. It is not what the graph approaches on the inside. Okay? So please don't have a problem if the graph approaches or crosses an asymptote somewhere in between. I didn't even sign test. Did I? Is that right, or is it the other way? Oh, no. How can it approach the asymptote if it was? Yes. Never mind. Do you guys sign test all this, or do you just kind of know? You sign test?
Better safe than sorry.
You guys are such hard workers. On the homework, would you sign test, or just on the test?
I would, yeah.
You don't even do the homework, dude.
I'm working on it.
All right, you got to know yourself. I look for repeated factors in here. If I had a square in here, what would that probably indicate around that point, whether it be vertical asymptote? Not necessarily bounce. It depends on if it's an x-intercept or vertical asymptote. But at a squared term, there will be no sign change, okay? So maybe if it's around an asymptote, it might be negative, negative. Or if it's around an x-intercept, it might be positive, positive, or negative, negative. All right? So think no sense. We cool? Mm-hmm. Okay. Let's try then a little harder. So this, let's get into the, you might prefer to write it this way, I don't know. Or even factor. What's that factored for? X minus root 2, or 2, I'm going to go 2 minus root x, 2 plus root x, because if you factor out negative, then you might have x minus x. But I call it that. Are we good? Are you with me?
Yeah.
Okay. What are the zeros then?
Wait.
Okay.
Yeah, numbers.
Just making sure you're paying attention. Way to go. That's the spirit. Okay. Root 2 plus x, root 2 minus x. Is that better? What are the zeros?
Well, back. Zeros plus roots.
Root 2, which is about what decimal? 1.4. You should know that. But you don't? I'm going to make you... we'll wait till later. All right. You're going to figure it out, Cody. Root 2 and negative root 2, about 1.4, negative 1.4. What about something else that's fun on the graph? Tell me something else. Vertical asymptote at 0. End behavior. As x goes to infinity, this goes to negative infinity. And as x goes to negative infinity, this goes to?
Negative infinity.
No.
Well, no, if it's going, oh, yeah.
Positive infinity, yes. Okay, now we'll actually get into that. Sorry. So the question is, all right, how does it go to infinity or negative infinity? So this is where we divide. In this case, if it's just over x, then you can divide easiest by doing what? Easier than that.
Separating.
Just wanted to see if you keep saying it. Separating, yeah. So if you were to separate these individually, negative x squared over x plus 2 over x, this becomes negative x plus 2 over x. Okay, now the idea of slant. You've never seen this.
I mean, yes.
Okay, not you. So this, although this looks vastly different than this, let's be clear, these are 100% the same. If I got a common denominator, I'm right back to where I started. They're the same. Are we cool?
Yeah.
So they have the same graph. They give you different things. This makes it nice to find vertical asymptotes. It makes it nice to find x-intercepts. But this makes it nice to find end behavior. Look at this. The limit as x goes to infinity of negative x plus 2 over x. Don't focus so much on this. Focus on this. As x goes large, that remainder goes small. And so this will start to approach just
Negative x.
negative x. Now that said then, this funky graph is like negative x as x goes to infinity. That's the slant asymptote. If I were to graph y equals negative x, then the graph is going to follow that behavior as we get larger and larger. If I sign tested on the far left, say negative 10, what's the sign at negative 10? Negative 100 plus 2 is negative 98 over negative 10. So positive 98. So you can see then, and if I wish I would have, actually let's do it. Let's compare. Just for the one-time case, I want to compare these two. So say at x equal negative 10, we said that was negative 9.8. A positive 9.8, thank you. And the line y equals negative x obviously would be 10, right? Okay. Now let's try negative 100. Way over there. What's negative 100 squared? Negative 100 squared. Please don't shoot that. 10,000. Okay.
1000.
Thank you. Negative 10,000 plus 2. Negative 9,998 over negative 10,000.
It's basically 1.
It's not 1. What is it? Negative 9,998 over negative 10,000. I know, you're killing me. 999.8.
Yeah.
Whereas the exact y equals negative x is negative, oops, that's not right. No wonder we're confused. I moved the 2 decimal place 2 times, didn't I? And so that's negative, or positive rather, 100. Now my point is this. If you look at around here, then there's a difference between our curve and the line. Okay, for small x's, there's a difference. But as x gets large, this difference here, 0.2, and then, I mean, it's practically nothing, and that's because the remainder starts to approach 0, and it really just starts to be closer and closer to negative x. So the graph is going to behave closer and closer to that function. Are you with me?
Yeah.
Okay. Adam's with me, great. Anybody else with me? All righty then. Let's talk between root 2 and 0. Say 1. If I plug in 1, what do I get? Or negative 1, excuse me. What's the sign at negative 1? Negative, right? And as I get closer and closer to 0, I'll be dividing by small, which will give me negative
Infinity.
large numbers, right? If I jump over 0 to a positive small number like positive 1, negative 1 plus 2 is 1 over positive 1. That's positive 1. So I got positives until I get to that x-intercept. And then after root 2, like 10, the negative 100 plus 2 is negative 98 over 10 is negative 9.8. So it starts to be negative numbers and it'll get closer and closer to 1. All right, now pause for a second and a couple fine points to point out. Are you with me? Any questions so far? All right, first, once you get the asymptotes, then I have people graphing this in funky, weird ways. So I might get a person that says, okay, I know my asymptotes are here and here, and I'll get graphs like this.
No, that's not a function.
Why can that not be?
It's not a function.
If I plug an x into the equation, how many y's do I get?
One.
I get 1, okay? So although it's funky, should this pass the vertical line test? Is it a function?
Yes.
Okay, so this kind of thing can never happen. I understand there's confusion, and where do I put the graph? For any 1x, there's 1 y. It's either here or there, not both. Okay? Second thing, if you're darn good, then the remainder is pretty darn informative here. This is what I'm graphing, okay? So the remainder will tell you where you are above or below the slant asymptote if you can think your way through it. At a positive x, so over here, is this remainder going to be positive or negative? Positive. So will I be a little above the line or below the line? Yeah, I'm like the line, my curve is like the line plus a little something, so I would be above the line. Over here, do you agree I'm dealing with 8 negative x's? Well, what's the remainder at a negative x? Negative, and so I'd be like the line, but minus a little something, so I'd be below the line, okay? That also tells you where you are in respect to the slant asymptote above or below. All right, so that's a rational function with the slant asymptote, easy division style. Any questions yet? Okay, go on to this one. This one's a little different in that the divisor isn't so easy as just a normal x. First, factorable top zeros, yes or no? Why are there no x-intercepts?
Because that squared term is always
X squared plus 2 has
not zero.
imaginary roots. That's exactly right. No real zeros. Okay? So not everything has to yield x-intercepts. That doesn't always happen. So no x-intercepts because it's not equal to 0. What about vertical asymptotes?
Negative.
Negative 1. Okay. Now the other behavior, the end behavior. I can see that because there's more power in the numerator, if I took the limit as x goes to infinity, the limit would go to infinity, right?
Yes.
Okay. To find the slant now, I'm going to say that first. I know that this goes to infinity. I need to find how by dividing. Now, if it's a linear divisor, like this is, x plus 1 is a line or a first power divisor, you can use synthetic, if you like. When I synthetically divide, because it's been a while, what goes in the box, whatever you might call it? Is it 1 or negative?
Negative.
It's a 0. The numerator's coefficients go up here. Don't forget placeholders if necessary. In this case, you have a placeholder for no x's, right? Right. So when I divide, I bring down the first, multiply, and record it in the next column. Add. Multiply, record it in the next column. Add. Now that's the divided out form. If I divide that out, then I get that y equals x squared plus 2 over x plus 1 is equivalent to
X minus 1.
x minus 1, and then 3 over x plus 1 is the remainder term. Now, you can get that power by saying if I divided x squared by x, I know the result should be x. That's how you know these powers. You with me? Yeah. So, that said then, this part, this is the slant asymptote equation that your graph will approach as x gets infinitely large. Now this whole thing is our graph. But as x goes large, the remainder goes to 0, and our graph will start to approach that sign. Did you have a question, or is that right? Okay. So if I were to place my slant asymptote, it has a y-intercept of -1 and a slope of +1. And I didn't mean to make that point, make it look like it's the point of the curve. So, we cool? All right. So in the far left region, and by that I don't mean all these regions, I just mean on this side of the asymptote, is it above the slant or below? You have two ways of doing it. What's one way to determine if it's above or below?
Look at the remainder.
Look at the remainder. I can look at the remainder. For the left side of the graph, I'm talking about an x below -1. If x is less than -1, then what's x plus 1? Negative. And so I'll be like the line minus something. And so will I be above the line or below?
A little bit below.
A little below. So I can tell that. If you don't like that, then you can always just plug in a number. Plug in -2 and see, what do I get? Plug it in here or there. At -2, though, you'll see you're up below the line. And so if I'm below the line and following those asymptotes, what kind of shape is it going to look like? I assume you're just doing it on your paper right now, yeah? Something like that, pass the vertical line test. Once I go past 1, then I'm going to get positive and positive. The top's always positive, the bottom will now be positive, and so the graph will look something like this. What's the y-intercept, by the way? Just for fun. 2, yeah? If x equals 0 is put in, and y equals 2. So the graph would look something like that. Yeah. Question? Okay, so that one was a little harder because we had to synthetically define the slant, but no big deal. Okay, this one then, starting to get slightly more complicated. This guy is, I should pause and let you try one. Let's factor it first to see, well, what's going on. If I factor the top completely, what's the numerator's factors?
X times x plus 2.
X minus 2. Okay, so that's nice. What about the denominator factors?
X plus 3.
Okay. Do I have any holes in this graph?
No.
Do I have any x-intercepts?
Yes.
Where?
0, 2, -2.
Okay, do I have any vertical asymptotes?
-3, 1.
Okay. Oh, that's great. Now let's get the end behavior. We know that the limit as x goes to infinity of this is infinity. So the question is, all right, what kind of path does it take towards infinity? I can't just anymore say, it goes this way. I need to be specific about how it's going to infinity. That's where we will find that guide by dividing. This, however, is not linear, so we cannot synthetically divide. We have to use long division.
Technique with long division.
Long division. You ready?
That's
X squared plus 2x minus 3 goes into
x cubed plus x squared plus x plus.
Okay, so let's get rolling. We look at the first into the first. How many times does x squared go in x cubed? X times. We multiply and record it below. X cubed plus 2x squared minus 6x minus 3x. Excuse me, minus 3x. Change signs. Draw the line. And subtract. X cubed minus x cubed is gone. That should always happen. We should gradually be working left. 0x squared minus 2x squared is negative 2x squared. Minus x, we can bring down the 0 next. And again, you start that process. How many times does x squared go into negative 2x squared? Negative 2 times. We multiply and record it there, then multiply negative 2x squared minus 4x plus 6. Change signs. Draw the line. And we get 3x I can't read my own
Minus
writing. Is that a
6.
6?
Minus,
Is it negative 6 or plus 6?
minus, because negative 3 times negative 2.
Plus
and
and
you
minus.
multiply.
All right, so the remainder is 3x minus 6 over x squared plus,
2x minus 3.
okay. Now, again, that's the equivalent form to that. They're equal, but they tell us different things. This form obviously tells us all the x-intercepts and the vertical asymptotes and all that good stuff. This form is what allows us to say as x goes to infinity, this remainder goes to 0, and the slant asymptote in it is that stuff in front. Y equals x minus 2 is the slant asymptote. So if I graph y equals x minus 2, then it looks like that. Cool? All right then. Start on the far left or the far right? What's your habit?
Left.
Okay, at far left point, maybe negative 5. I'd have a negative, 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 5 negatives is
Negative.
negative. So how am I going to be negative and follow these asymptotes on the left side of negative 3?
You would have to be in that little part.
Can it be here?
No,
Why not?
because it would cross the x-axis.
Yeah, there should be an x-intercept and a sign change, and we know I don't have that, right?
Yeah.
So it has to be a little e.
So the only way, oh, shoot.
No.
So the only way, I'll just erase it. How's that sound? The only way to make that negative only happen, no x-intercepts, is to be down there. Okay? You could sign test, but because I don't have any linear factors, or specifically because at negative 3, I know I'm going to change signs, then the overall outcome will change signs. So instead of negative, now I'm going to be positive. Likewise, when I jump over negative 2, it's not squared, so there's going to be a sign change, and I'll go negative. And then when I drop over 0, it's not squared, so there's going to be a sign change, and I'll be positive following that asymptote. After 1, I also see that's first power, so I'll change signs and be negative. And then after, it'll be positive and 0. Now, I'm not going to grade for above or below the asymptote, but looking at a number greater than 2, would I be above or below the asymptote? Number greater than 2, that remainder is going to be above the asymptote. So I really should be above, but as long as you're calling asymptote. Yes?
So can you make a pointy, like, you understand, could you make it?
This?
Yeah.
So if you are a pre-calculus student, I wouldn't take off for making it pointy. But because you're a calculus student, why is that not okay to be pointy? It's differentiable, so it should be. Okay. I don't care how smooth, but it shouldn't be too. Don't make it too pointy, I guess is my.
Is the remainder, like, always the indicative number that goes above or below the...
For polynomial rational inequalities, yes. If I had E in here or something that's not. Okay. Last one, or maybe we should. Oh, no, you need. Sorry, no offense. This one's a little ugly. So tell me about x-intercepts here, people. -1 and root 2, 1.4 and 1.4-ish. Wow, those are really close together. I didn't mean to put those so close together, but it is what it is.
You could change the scale.
Shall we? I don't know what the other asymptote's going to happen like. So vertical asymptote at
1.
Okay, so let's talk in behavior. What do you say? What do you say? This is the same as x cubed plus x squared minus 2x minus 2. Overall power-wise, this is like x cubed over x, which is roughly x squared-ish. So as opposed to this, which were x cubed over x squared is x-ish, so linear, this x cubed over x-ish will start to approach parabola. Yeah, it'll have a parabolic asymptote. Let's divide, shall we? Synthetically or long division? Synthetic. If you do synthetic, then you get something like that. So what's the equivalent form of this rational function?
X squared plus 2x.
X squared plus 2x
Minus 2 over x.
is 2x. Oh, man. I want the equation of that parabolic asymptote. Parabolic asymptote at what? What happens to the remainder? And so the parabolic asymptote is? X squared plus 2x. Do you want to complete the square and put it in standard form, or use the factored form of that parabolic asymptote? Factored form it shall be. Okay, so here's where colors come in handy. I have a parabolic asymptote with zeros at 0 and 2. And the graph would look like, that's what I said, -2. Oh, shucks. Man, this is going to get convoluted. Do I misunderstand this button? This button is supposed to undo, right? That's the undo button, right?
Are you scrolling? I don't know.
What the heck? All right, forget it. I might need to calibrate it. So 0, -2, yes? So here we go, 0, -2. The graph looks like this. Okay, far left side, what's the sign? At a -5, what would you have? Positive or negative? Positive. Okay, that's good because it's supposed to follow this graph, right?
Mm-hmm.
So if it follows that parabola, I'm not going to sweat above or below. I'm just going to follow the parabola. We can get into the finer points later. Although, yeah, that's right. Let's just. Is it going to be above or below over there?
Above.
At -3, -5, it would be above. So it should actually be writing a little above, but that's okay. What do I then come to hit? Next thing I come to graphically is the x-intercepts. And so that x-intercept, I have to pass through that, and then what? And pass through the other one, so it's going to go below for a little bit, and then above, and then what happens? Does it follow the slant or the vertical?
It'll follow
the vertical. Remember that slant is only for the outsides. And so we follow that, and then last but not least, what's the graph going to do right of the vertical? Follow the slant here. What about at the x-intercept? We'll follow the vertical asymptote. So you get something like that. Isn't that fun? Yes. All right, the ones on the homework. This, by the way, parabolic is not in the Saxon book. But I like to throw them in, so I just won't shoot you disadvantage. That's it. Boom. Good. Well, let's see. I thought, as usual. Let's see. Questions on sex. Should we do a page of the test? Yeah.
So what set did you guys do?
I actually wouldn't mind some help on Saturday.
Okay. Before I head out the test to look at, but let me communicate in terms of due dates and stuff. We need to get caught up. So this is the expectation. What's the oldest thing you have? 77? Set 77 is due today. Okay? Tomorrow, Tuesday, 78 and 79 are due. And Wednesday, 80 and 81 are due. We will get caught up by Wednesday. That's it. If I get to all the questions, great. If I get to none of the questions, fine. But I'm having people say, oh, I don't have to do homework now. You're not really, there's a couple people that don't get it. I will be happy to put the keys online to help you towards that end. And if you're foolish enough to just copy them, that's going to be on you. But I'll get you. Don't you worry. Yes, we have a question?
Yeah, so Bruce and I, when we left on Friday, we didn't check the statistics.
That's fine. All right, here comes the first page of the test, the second page of the test, which is still Oh, sorry, by the way, did I get back? Oh, here's a bunch of homeworks too.
Mr. Ripley,
Yes.
I'm confused on how
Keep them crosshatched, please.
Yeah, I can actually get some correct math.
shouldn't the like this time
I don't know what.
Let's think of this Oh, sorry. If I wanted to put this back together, I could say the common denominator would be x minus 1. Then I could multiply, get that common denominator like this by x minus 1, like this by x minus 1, like this was
so just this entire thing is equal to
this, no, this one, yeah, if I get common denominator, then you would add that to Ryan? Salva? It's not good at Okay. This one will have fractions on 1, A, and B.
Oh, really?
The back one, yeah. 1, A, and B,
One
the back one,
A and B.
correctable one's back. Do you have time to talk about this a little bit, or just, let's see. Maybe we can at least get one corrected, shall we? We need extra practice on this. It didn't go awesome. Maybe I should. Yeah, this is going to take a little longer than 4 minutes to get done well. Let's see what let's get one done, shall we? All right, for number 1, you have to be good with expanded form, which is what they're giving you. Summation notation, and definite integrals. You need to be able to move seamlessly from one into the other. The big idea for both of these by far is that the base is factored out and you have the heights in here. Whether it be factored form or expanded form. The base always comes from the total region divided by how many chunks. So the base will always be some kind of something over n. This tells you the region width or the base of each rectangle. You follow? All right. The inside is the heights tell you then what the function is. And it also tells you the starting point. Now for this problem, if there's a 1 out of 50 or 1/50th out front, then surely the width of the regions is 1. Okay?
Yeah.
Unless they're really messing with you and giving you a fraction that reduced. So that each base is 1 wide. Or each base is 1/50th wide, and the width of the region is 1. Now, obviously, there's a lot of regions with width 1. Is it 0 to 1, or is it 1 to 2, or is it 3 to 4? I mean, I can get a million regions that are 1 wide. Yeah. The inside is what tells you what did they start at. If you're supposed to go 1/50th over, and the first x you put in is 1/50th, then they must have started at 0. Because if they had started at 1 and went over 1/50th, what would that first x be? You start at 1, go over 1/50th, would that first x be 51/50th? So 1 and 1/50th, right? Are you with me?
Yeah.
Okay. So the fact that I see 1/50th in there tells me that I know the region starts at 0. And it also tells me that it goes up to 50/50ths or 1. It must be 0 to 1, yeah?
Yeah.
So I know the limits of integration have to be 0 to 1. Unfortunately, that didn't rule out much. It only ruled out the last. Okay? Second, don't think that this 1/50th is actually in the function or out front of the function. That's just the width. If I found the area under the curve from 0 to 1 by an integral, there wouldn't be a 1/50th in there anymore. It would just be the straight up area under the curve. This 1/50th, people say, well, where did it go? This is the width of each region, as we said. When you take infinitely many rectangles, where does the width go? It's the dx, okay? So don't think, oh, there should be a 1/50th in my work. There should. The 1/50th becomes the dx as you take more and more rectangles. The inside is just a bunch of straight up, what is the function? Now I understand if you think, oh, so it's got to be x over 50,
No.
but really the 1/50th is, we talked about the width of each region. It's just straight up 1/50th into the function. 2/50ths into the function. 3/50ths into the function. So what's the function then? It's just straight up root x. Okay? Now, I know I'm rushing this, and you might still not be totally locked in, and we will practice it some more, but that's at least the start. I need this back. Please hand it to me on the way out. I will give it to you back tomorrow, and we'll go over more tomorrow. Make sure you get 77 people.
What was the correct?
It was 16,000. 1.8 for 2 people. I mean, have that on the
Kate Sullivan and Daniel Burke, the attendant's office.
All right. Thank you. I hope so.
So you must be the first one.
Thanks, sir. Have a good day. Well, he's trying, man. Jeez Louise. Says let's go. It's rushing. Thanks, sir. Have a good day.
I'm so excited for washers.
Rushers is tomorrow.
Not this again. Hate this.
I hate a lot of things.
But I hate that this changes every month, and I don't know what I'm doing now.
Oh, that's not.
Oh wow.
Oh, wow.
More different than it usually is.
I like this.
I don't.
Oh, shoot. Forgot to pause this.
What are you doing?
Mr. Bickman.